Hello, my name is Yinghaoden. My project name is Deep Survival Prediction for Colorectal Cancer Patients from Imaging and Non-Imaging Data. In this, my supervisors are Gustavo and Gabriel. In this presentation, I will go through the problem, the methodology path, the results, and the future works. Let's start with the problem. The colorectal cancer has become one of the most malignant diseases in the world. The patients who diagnosed with colon cancer have only about 10% of 5-year survival rate. And the prediction of colon cancer is quite difficult, as it mainly relies on benign polyps, which develop into malignant tumors over a different amount of time. And colon cancer is divided into the criteria of the infiltration depth of the tumor, the involvement of metastatic lymph nodes, and the presence of metastasis. The currently metastatic lymph nodes are usually diagnosed by CT, followed by surgical removal of the tissue and a laboratory examination to detect cancer cells. So making diagnosed based on CT imaging is quite difficult, and positive lymph nodes can be easily overlooked. So we developed our deep learning model to detect metastatic lymph nodes in the early stage in order to detect colorectal cancer. Methodology part. The dataset we use in this project is provided by Royal Artillery Hospital. It contains 539 3D axial CT images with classification labels. The negative means no metastatic lymph node detected, and positive means there is metastatic lymph nodes. And the CT images have different size of slices for the third dimension, the depth, and we uniformly adjust it to the same size of slices to make all image size consistent. So in this project, we resized all the images to 96 by 256 by 256. And the dataset is split into 3 parts: training, validation, and test. Training takes 70% of the images, validation takes 10%, test takes 20%. We also consider the proportional number of negative and positive images in each set to make sure each subdata set is on behalf of the entire dataset. Models. We use DenseNet as our baseline model. For each layer, the feature maps of all preceding layers are used as input, and its own feature maps are used as input into all subsequent layers. DenseNet have several compelling advantages. They elevate the vanishing gradient problem, strengthen feature propagation, encourage feature reuse, and substantially reduce the number of parameters. And dense block consists of a batch normalization layer, an activation value layer, and a 3 by 3 by 3 conf layer. And here's a dense block with 4 dense layers, and followed by a transition layer to reduce computation load by reduce the parameters numbers. Here's the GC block. GC block is global context block. It's one instance of self-attention mechanism. And GC block has 2 advantages. It has lightweight computation. You can see from here, we have 2 bottleneck reduction ratio to squeeze the network squeeze down to save computation no work, and so it can effectively mode long-range dependencies. So in this presentation, in this project, we use GCBlock to optimize our model performance. In each training epoch, the after training process done, we validate the model using validated set. We can update our best model based on validation loss or validation error, which is accuracy. So in the following experiments, two criteria will both be tested. The graph on the left shows the DenseNet baseline model. The graph on the right shows DenseNet with GCBlock. Let's see the results. There are two colors here. The strong yellow color means baseline, so the baseline with GCBlock. The transparency color is baseline performance. So you see from the graph, GCBlocks help training loss goes down. Yeah, and on the graph on the right, the GCBlock helps training AUC goes up, and it helps the validation AUC goes up than baseline. So this one is comparison best model based on validation loss. You see the loss has validation based on validation loss is much better than validation error. So you see from the graph, the GCBlock helps training loss going down and helps validation loss squeezed into a certain range, not going up and down. And the graph on the right shows GCBlock actually helps training AUC goes up, maybe up to 1, and also helps validation AUC goes to a peak. The peak is far above the baseline model. And test result on test set. If the best model is selected by validation error, GCBlock helps training test AUC goes up 0.04 and helps the training loss converge. And if the best model select criteria is validation loss, GCBlock helps test AUC goes up about 14%, and it helps conversion with high speed. Next step, future work. So if I have more time, I will use large resolution images for model training if possible, and update the best model only based on validation loss instead of validation error. That's bad. So maybe you want to try maybe update based on validation AUC. I don't know what's going to happen, but it's worth a try. And we can also try different hyperparameters like bottleneck ratio, and try other proportion of training validation test set, and try maybe other neural network models. Maybe they're going to help. Any questions? Thank you.